So how can we figure out what's going on here? I mean, in the previous video, I basically kind of, took that circuit in here, called a real test, I ran it through the Burlington machine, and I also ran it through a what was that? I think I ran it through the simulator, but I can't see. Oh, yes, I ran the real test against the backend, which was the backend was the simulator. Yeah, it was the simulator. And so it seems to work on the simulator, but it doesn't seem to work on the real quantum computer. Yeah, basically. That's the current situation. And I have no idea how can that happen. So task for now is clean that up. Let's clean that up. That's the first thing. So yeah, so basically I'm gonna start by, I think there was an import somewhere in here. I was doing the load account, all the stuff I should be doing. I should be doing these, I think, at the very beginning. So I'm gonna get that in here. I'm gonna get rid of this cell. I'm gonna get rid of this cell. I'm gonna put all that in here as well. So the edges for, I mean, that's obviously the same. Good job. We don't really need a print data, so I'm gonna delete that. And so what we need to do is, so we're doing is, here's the oracle. Here's a quantum circuit that's not needed, definitely. QC draw is also not needed. And so that test is also not, we're just testing in here. So I think this bunch of visualizations are not needed either. Can I just delete like that? No, I gotta do, there's no shortcut for deleting the cell, delete the cell. So now here we're preparing the RTOF, the RTOF-M, the TOF-S. I mean, we're gonna keep those ones in there. Then we're doing the amplitude amplification, which we finally got it to work this way. And then we're doing the final test. But now I'm gonna basically get rid of the final test as well. So we're gonna, can I select more than, I can select more than one cell. Final test, final test, final test. Gone. We're done with final tests. Done with final tests. Delete cells. So we're getting that into instruction, then we're getting a real backend. We are getting the coupling map and all this kind of stuff is also not needed. So I'm gonna just getting rid of these things. Then we're creating the real test circuit in here. Should probably change some naming. And then what am I doing? So I'm getting the backend again. Not again, but I'm actually getting the, okay, so here I'm getting the orange, which I don't want to get anyway. So I'm getting the Burlington, so I'm gonna definitely delete that, getting Burlington. This definitely goes away. So we're just doing some cleanup in here, okay? So what are we doing? Real backend. I will not call it real backend. I'll call it a Burlington. And this will be Burlington job. And so the real test is going to be circuit. Call it just circuit. So we'll just call it circuit, and this is a circuit, and then there's going to be this circuit, then it's going to be a real job, and then we're basically, I'll just call it hist1 with the Burlington job. I'll just call it Burlington hist. Burlington job get result get counts. And that's also not needed. Here we're applying this. And now I'm getting so I'm gonna merge these things here. I'm gonna also basically do something like, this is the Burlington, so this is the circuit, and oh yeah, backend. So I got rid of that. So simulator, I'm gonna basically get the R get the backend chasm simulator, and so it's gonna be the simulator, not backend, and we're gonna do both 8,192 shots. Simulator job. Simulated job, and basically print status of the simulated job, and then get the, so this is gone, this here is gone, and so we're getting these things in here as in like simulator hist with the simulated job. Just cleaning it up a little bit, okay? So and we'll plot them separately right now. So just put it separately, and so this and this all go. Yeah. So I'm not gonna draw. This circuit is useless to draw. So circuit. Oh yeah, it's not defined because I haven't really run that there. So here it's important for me to print it. These I also want to have drawn. This doesn't have to be. This doesn't really have to be drawn. Good, looks good. So now it's a bit cleaner. Let's see if I now basically do a restart the kernel and restart all the jobs. We'll see what happens. So that should do something. Kernel idle. With dialog. Restart and clear output, restart and run all. Yes, okay, now it's being all executed. I don't know why I even got the edges here. So So this is sort of a we cleaned it up, but I nevertheless uh, wanna play with another circuit maybe, and validating. So let's see what happens. I mean, probably the same will happen, but it's just, what I want to do is I want to try to kind of now take a look and then maybe try a couple of other circuits and compare the Chasm simulator and the IBM Cube Arlington. But at least this way I have this sort of clean, and then I can also, put that somewhere, maybe ask, share that notebook in the Qiskit Slack and ask what's the, you know, what's sort of the difference. Wait a second, why didn't this plot the two things? It just plots one over the other, I guess. Simulator hist. So I'm gonna do this, and I'm gonna do color blue, green. Oh, well, okay, so that doesn't. It's keeping the same results. Okay, so let's do the following. What if I try something else? What if I say, good, like for example, what if my quantum circuit, right? What if my quantum circuit is cell below, and I say circuit is quantum circuit 2, okay, I'll just do a basic entanglement. So I'll just basically now say circuit Hadamard 0, circuit control X 01, circuit measure 01, 01, circuit draw output equals MPL. Just let's do something simple. So I draw this circuit, just your basic entanglement. And now let's kind of, those things honestly should be right at the beginning of the they should be just here. So done with this, and then this is just now going to be the circuit creation, the job execution, the status printing, and then basically that can be a single cell. 8 cells. So anyway, we've got this. We run this thing. Quote, let's see, running done. So let's wait until they're both done. And we should see clearly that's a fairly simple circuit. So running in Burlington. Let's see. So running in Burlington. Burlington 5 qubits. U2 error gate. Maybe those colors are those colors indicating kind of like the current error rates. I mean, that's quite cool, honestly. Let's see. Are we done? We're done. It's time to plot. Fairly okay. Fairly okay. Still. Okay. Huh. Still the rest is just, so the same circuit doesn't seem to work at all. Maybe I gotta pick up another, I don't know. What about London? Let's go with London. IBMQ London seems empty as well. So I'll add London. I'll add London. And so we'll get basically the London job. The London backend. So we're gonna print the London job status, and we're gonna get the London histogram. London hist, London job result, and we're gonna also print London, and that's gonna be red. Good, but now first we'll do this. So let's try again this circuit. So current status of those jobs, running, queued in London. Yeah, I think I'm going to be doing a bit of pausing in here because it doesn't make sense to make you guys wait for these results. It just feels unfair. So let me just try again. Running, queued. Okay, I'm gonna pause the video now, and then I'll just come back once it's done, and we'll give it another try with that big circuit. But it's awkward that it doesn't really kind of work. But it seems to work in the paper, right? I mean, the results are definitely there. It just doesn't work at all. Attempt done, cute. Yeah, good. I'll stop for a second. Okay, so it's kind of done. Seems to be, London seems to be way better. Let's get rid of this for now. And let's try with this circuit. So this circuit, and then let's get, we'll add 2 more zeros. I don't know if that's a typo. I think so, because that's a lot of shots. But let's see. It's a big job. Oh, error done. Yeah, it's too many jobs. That's a typo. So like this. That was 20 shots. Running, cute, running. Cool. And now I'll let that running as well. So I think, though, there's one thing here that caught my attention now. So it says this results. Okay, this is sorry. Yeah, that's definitely a typo. So I think this circuit. So let me Give me a second. I'll open the Google Docs for feedback. So I'm kind of collecting feedback in here. So there's another point which is basically typos, I'd say, on the experimental results section. You mentioned many times you've run this circuit with shots, which it's a typo, and you probably meant, yeah, that's correct. So still running, and basically, but look at this. So okay, so there is basically a 2-qubit mapping were tested for each circuit. Each circuit is executed times with measurement error mitigation. What is these? Measurement error mitigation, Qiskit measurement error mitigation. I don't know. I recall having seen that in one of Abe's videos. Qiskit error mitigation in Qiskit. Oh, it's in the textbook. Okay. The effect of noise is to keep, but let's go through this. So where is that? I mean, I'll go through this eventually, I guess. Okay, so it seems there's some error mitigation you can apply for this to work. Let's take a look at this. The effect of noise is to give us outputs that are not quite correct. The effect of noise that occurs through our computation will be quite complex in general, as one would have to consider how each gate transforms to affect each error. A simpler form of noise is that occurring during final measurement. At this point, the only job remaining in the circuit is to extract the bit string as an output. For an n-qubit final measurement, this means extracting one of the 2 to the power of n possible n bit strings. As a simple model of noise in this process, we can imagine that the measurement first selects one of these outputs in a perfect and noiseless manner. And then noise subsequently causes this perfect output to be randomly perturbed before it's returned to the user. Given this model, it is very easy to determine exactly what the effects of measurement errors are. We can simply prepare each of the 2 to the power of n possible basis states, immediately measure them, and see what probability exists for each outcome. As an example, we'll first create a simple noise model which randomly flips each bit in an output with probability p. Okay, let's take a look. So what does this mean? Okay, now that gets interesting. Cool, some interesting stuff here. So I'm gonna new notebook. I'm gonna do a new notebook with error mitigation. So let's see that. What's going on here? So we're importing providers error noise model, Pauli error, depolarizing error, get noise p error, measurement Pauli error, whatever that means. Noise model. At all qubit quantum error. Measurement is applied to measurements. Okay, so with probability p, it applies a bit flip, and with probability 1 minus p, it does nothing. That's what the noise model is doing. Pauli error. Okay. I think that's what it means. So, and then it adds this error happens to all qubits. Okay, so let's start with an instance of this in which each bit is flipped 1% of the time. So we get that. Oh, now we get it. Now we can test out its effect. Specifically, let's define a 2-qubit circuit and prepare the states 0001, 1011. Without noise, this would lead to define outputs, blah blah blah, respectively. Let's see what happens with noise. Here and in the rest of the section, the number of samples taken for each circuit will be shots 10,000. Okay. So let's first take a look at what this is doing. So for each state. So you're creating a quantum circuit for each state. Let's define a 2-qubit circuit and prepare the states. Shouldn't these be... So if state 0 equals 1, QC x1, if state 1 equals 1, QC... Okay, so you prepare... you prepare a quantum circuit with each of those starting states. Then you measure, and they say print state plus becomes, and then execute the quantum circuit with a Kazan simulator, and you give it the noise model. See what happens. Oh, quantum circuit, because from cascade import all. So 0, 0 becomes 0, 1 87 times, 1, 0, 100. Oh my, that's interesting. Okay. Okay. Okay, that so far makes sense. We're just making up a noise model. Here we find that the correct output is certainly the most dominant. Yeah. Ones that differ on only a single beat, such as in the case of or occur 1% of the time, does differ into qubits only a handful of times in 10,000 samples, if at all. So what about if we run a circuit with the same noise model and got a result like the following? Boom. Here, 0, 1, and 1, 0 occur for around 1% of all samples. We know from our analysis of the basis states that such a result can be expected when these outcomes should, in fact, never occur. But instead, the result should be something that differs from them by only 1 beat. Okay, so I think this is going now to be like, we're going to do some sort of correction based on the noise model. So we're going to say, in 1% of the cases, this should be tweaked and should be back to either 0, 0 or 1, 1. So when we look at the results for those two outcomes, we can see that they occur with roughly equal probability. We can therefore conclude that the initial state was not simply 0, 0 or 1, 1, but an equal superposition of the two. If true, this means that the result should have been something along the lines of 1, 1, 0, 0. So what if we run a circuit? Okay. So what if we run a circuit? I thought we were doing the same now. I don't know why. I got lost. Okay, so we're now running a circuit and we just get that. Okay, yeah. Here's the circuit that produces results like these up to statistical fluctuations. And that's the circuit we're just playing with. So that's the, okay. That's the Bell state, but now we're doing it with that noise model. So it does this. By the way, is this done? Yeah, it's all damn flat. It's all damn flat. Maybe that's the point of it all. It's really the noise model in here. What's missing, you know? It's flat. Okay. With error mitigation. In this example, we first looked at the results for each of the definite. But if that's true, that means those computers are shit, man. Sorry. I mean, again, it's like it's a big milestone to have something like that, but it's pretty crazy that you got to apply something like it's pretty crazy that the noise is so much. Let's see, okay, but let's see. Let's not take on any conclusions, draw any conclusions too early. So we got that. In this example, first look at the results for each of the definite bases and use the results to mitigate the effects. Wait a second. Is it noise model, noise model? Have we corrected anything here? I didn't see. In this example, we first looked at the results for each of the definite basis states and use these results to mitigate the effects of errors for a more general form of state. This is the basic principle behind measurement error mitigation. Measurement error mitigation. Is this the one that they're talking about here? Yes, measurement error mitigation. I think that's too okay, but they mentioned that though. They do mention it, so I was not aware you could do that. Still, is this really? Plot histogram. Do I need to import that as well? Plot histogram. Nice. Get counts. Plot histogram. Ah, okay. But hasn't been correct. If I don't add this, then it's perfect. This hasn't been corrected. This has the noise. Where is the correction? Where is the correction? Measure. I'm missing here the. So this is the. So then here comes the math, like. In this example, first look at the results for each of the definite basis states and okay. But I don't see where the mitigation has been done here. Now we just need to find a way to perform mitigation algorithmically rather than manually. We'll do this by describing the random processing matrices. For this, we need to rewrite our counts dictionaries as column vectors. For example, dictionary describing would be like that. Here, first element is 0, next 0, 1, and so forth. The information gathered from the basis can be then used to define a matrix which rotates from an ideal set of counts to one affected by measurement noise. This is done by simply taking the counts dictionary, normalizing it, and then using it as the first column of the matrix. The next column is similarly defined by the counts dictionary obtained for. Yeah, okay. The stuff that we print becomes 0 becomes this, 0 1 becomes this. Okay, yeah, and then you're just multiplying and adding that. So if we now take the vector describing the perfect results for a given state, applying this matrix is as a good approximation of the results when measurement noise is present. Correct. Yeah. So now we do this in here, the math way. Applying. Ah, okay, I see where you're going. And so you're going to apply the inverse of that. Ah, smarty. Oh, you smarty. You're going to apply the inverse of the noise model to kind of correct the results. Not bad. Not bad. That is, I didn't expect to be diving into this right now, to be honest. So this is noisy stuff. And then, what is it all doing? SciPy linear algebra, then we've got the matrix. And then applying the inverse. Okay, so here's calculating the inverse. No, here's, okay, the inverse is already calculated here. So this is the inverse time dot product of inverse and noisy. And then you get the mitigated results. Pretty smart. First counts should be integers, and so the values need to be rounded. This gives us a very nice result. Cool. Okay. Error mitigation in Qiskit. So now there's going to be like, okay, so now, okay, what's this now? So the process of measurement error mitigation can also be done using tools from Qiskit, of course. This handles the collection of data for the basis states, the construction of the matrices, and the calculation of the inverse. Awesome. The later can be done using the pseudo-inverse, as we saw above. However, the default is an even more sophisticated method using least squares fitting. As an example, let's stick with doing error mitigation for a pair of qubits. For this, we define a 2-qubit. Okay, so we're going to import some new stuff in here. Ignis mitigation measurement, completeness cal, completeness feeder. To process the measurement. Okay, as an example, let's stick with doing a quick mitigation for a pair of qubits. For this, we define a 2-qubit quantum resistor and fit it into the function completeness cal. No chances I memorize all these. Cal state labels, completeness cal. So that's probably something that does kind of this part in here, I'm assuming. I guess. This creates a set of circuits to take measurements for each of the 4 basis states. So this creates this mass calyps. Okay, 00 x, so 0010 0111. Let's now run the circuits without any noise present. Okay, so what is it doing? Custom simulator. Good. With the results, we can start the calibration matrix, which we have been calling M. Okay, I mean, those are ideal results, since obviously 111 with no noise present is simply the identity matrix. Now we're going to get the noise model. We define above with 0.1. We run the same circuits, but with this noise model. Cool. This time we find a more interesting matrix and one that is not invertible. Let's see how well we can mitigate for this noise again. Let's use the Bell state. But where's the mitigation happening in here? In Qiskit, we mitigate. Okay, so that's the noisy circuit. And now it says, in Qiskit, we mitigate for the noise by creating a measurement filter object and taking the results from above. We use this to calculate a mitigated set of counts. Qiskit returns this as a dictionary so that the user doesn't need to use vectors themselves to get the result. Mess filter. There's no chance I remember any of this. Mitigated results, mitigated counts. To see the results most clearly, let's plot both the noisy and the mitigated results. The image just looks nice. Okay. Legend noisy mitigated, noisy counts, mitigated counts. Noisy mitigated. Interesting. Interesting. Here we've taken results for which almost 20% of samples are in the wrong state and turned it into an exact representation of what the true results should be. However, this example does have just 2 qubits with a simple noise model. For more qubits and more complex noise models with data or data from real devices, the mitigation will have more of a challenge. Perhaps we might find methods that are better than those Qiskit uses. That was really insightful. Now, my question is, how do we do this? How do we apply this here? Well, doesn't the actual QC have, like, can I not get the noise model of a real device? I think I can get a noise model because I remember doing that noise model. I think it was in here. Noise model. Basic device noise model. Noise. Device, basic device noise model. Properties, real device. Ah, exactly. Okay, so I got my real device. Okay. So let's do this. Let's do this. We've got actually the histogram data here already, right? So if I say print, for example, we're gonna take a look at the Burlington hist. So we got the counts in here, but now we're gonna do error mitigation. So first of all, we've got the Burlington guy in here. So we're gonna basically try to get the properties of Burlington and the configuration. So there's going to be Burlington properties and Burlington coupling map. And now what we're going to do is basically, so what's next? So now I got the properties. Now I need to create a noise model. That's the noise model. Okay. So basically with these things in mind, so maybe I'll put all that at the very top. Noise. And so now I'm doing a noise model. So now I got a noise model, not from properties, but from Burlington properties. And honestly, you should say Burlington noise model. More consistent. So now we got the now we got it. So now we got the noise model. So now I just gotta basically copy the stuff that I've been doing in here. So I'm probably gonna have that then in there as well. So this is gonna be here the inputs for noise. And so we're gonna now basically we got that. So I think we can just skip now to that part in here. Now that needs to be imported as well. Inputs for noise. And so we're now gonna have to, so we're gonna have to do it for, we got 5 qubits. So we've got 5 qubits. And let's hope that works. Okay. QR. So if we print the circuits, then we should have all these different possibilities in here. Yeah, okay, makes sense. Yeah, I'm gonna delete that actually. Delete cell, that doesn't interest me. Now, we've executed, we've got the results already, okay? So what we need to do now is we want to take these. What are the cal results? Are the results from the with no noise? Okay, so now we're gonna take a look at, we're gonna create this filter thing with the so what are the results? It's just a job result. Okay. So we probably want to get also we probably want to do insert a cell above and just get the results. So results, and get rid of the counts. So this has been then there. So now I'd like take Burlington results. Do that these state labels are already here. Circle label, I don't know what this means. Let's see what happens. Yeah, well, I don't know. It's all zeros. That's awkward. So it's not cal matrix what I want to do. It's a calibration matrix. Yeah, that's what I want to do. Yes, feeder Burlington results, state labels, Burlington results. Are these results really just the cal results? Is job result? Okay. So that's definitely not what I expected. So what am I doing here wrong? Burlington results. So this is currently being plotted correctly. Burlington results. Burlington job dot result. Yeah. Properties. Noise model, noise and environment properties. Cascade quantum is a 5. QR. State labels, Burlington results. It's all zeros, or maybe it's not all zeros, but it's just, I don't know. Let's go ahead. Now you've got your noisy counts that we don't care about these. Now we get the filter object. So MEAS feeder filter, MEAS filter mitigated results. Apply results, but where is results coming from? To the actual results, to the actual Burlington results. Burlington results, but how do I call results? Job results. The noise model, chasm simulator. Well, I'm at the point I feel I'm not like reasoning. I don't know. I'm just probably just shooting words. I'm just trying to understand this as I go. So results are the noisy results. But I'm kind of thinking here that I see, I see, I see. Mass Calyps, these things have been... Maybe I missed the cal results. Have I done that? I haven't done that, I think. Execute the calibration results without the noise. Have I done this? I haven't done this. That's what I'm missing. That's why I get all zeros. So this is right after creating that. So I'll just do it like that. You get a simulator, you run all this kind of stuff, so you get the cal results. And so these cal results go here. And so, right? Exactly. And then you're applying that to, yeah. So this is done. This is done. Yeah, but it's all once. Then I don't know. Sorry, I gotta, not without the noise, with noise. Come on. Sorry. Noise model, after the shots. Burlington noise model. Noise model equals this. So we now run that with Burlington. Oh, yes. Okay, so we're now running. Okay, so now we got something. And now we get basically these, and we apply not to results, but we apply to... Oh my God, that's that I'm getting lost in here. Cal results. Now we apply to the Burlington results. So we apply to the Burlington results, filter to the Burlington results, and we get the Burlington mitigated results and the Burlington mitigated counts. Yes. And now we basically do plot histogram this. And now it's the moment of truth. Let's hope this works. What happened? Plot histogram. What am I missing? So I gotta print it like this. Plot histogram, noisy counts, mitigated counts, legend. No, I don't think I need all this. Value error. Invert x-axis max, arc is an empty sequence. Problems and mitigated counts. Whatever, I'll just do it this way then. But we're just Burlington, we're just printing the elections. What's wrong? Did I do print mitigated counts? By 0. apply it to Burlington results. I don't get it. It's an empty. So we got that mass feeder. Then we get the filter applied to Burlington results. And Burlington results is Burlington job result. Maybe I gotta rerun all the jobs. Gotta rerun these things. Maybe I'll give it a try. Okay, so let's give it a try from here. So we're not gonna do London. 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 Yeah, and the rest is just that. Okay, so we're doing this, validating and running. It's good. That's gonna be a long video. Running. Uh, Still running. Can't believe this. Can't believe this. Burlington job. Get that like that, I guess. So, just to be consistent, yeah. So we're done. We get the results. And we don't do. Hold on. Hell. Okay, I think I gotta. I think I got. I think I gotta refresh the whole thing. That is why 5. Oh, by the way, that should be 4, not 5. That's for sure. But have I maybe mistakenly played with QR or something like with the? Have I clashed anything in here? No. Why am I getting 5 qubits when this guy has only? Let's do it this way. Let's save this. Let's interrupt the kernel. Run the kernel. No. Interrupt the kernel. Kernel. Restart. Run all. Okay. That sounds like a better idea. Yeah, I'm gonna let me stop the I'll just pause. Oh no, it's going on already. It's going on. Boom, 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 boom. Where are we? Validating. Burlington job. Get counts. Come on, that really should work, you know. I'll pause here, okay, because it's gonna be too long of a video otherwise. So now we got it. Yeah, I think I just probably had messed up with something by re-executing some of the cells. So now we got here something quite interesting. What happens if we plot this? That's a good question. but I'm not so sure. Plot histogram. Arlington mitigated counts. Let's see what happens. Ah, come on. Are you kidding me? There's no fucking difference. Okay. But it must be somewhere along those lines. So there has to be some sort of, there's definitely some sort of error mitigation here that needs to be done. I mean, and it seems like this is working. It seems we've got this filter thing here. Hmm. So what if I plot the Burlington Hist? So I'm gonna plot. What if I plot the mitigated counts in green? Red and green. Sorry. This is gonna be Burlington Hist. It's like you're kidding me, right? Okay. Hmm. Yeah, the output is too equal. The output is too equal, right? It seems it's not just. I think the error mitigation had to be done anyways, but I think it's not like there's something off with but the circuit works in the simulator. Why doesn't it work otherwise? I mean, it works in a damn simulator. Good. Yeah, that was a good attempt, though. At least I caught that measurement error mitigation thing. Uh, uh, uh. Error bars represent the standard error runs with phase shifts that will compensate for later in the algorithm. This technique is exact and will benefit a broad range of these things. Okay, just the text here. What is that? KL divergence. This is quantum volume. Okay, so, but I'm still not getting the results that I want. Eh, that's not good, but it works as a simulator. Gotta figure this out. Anyway, I'll leave the video here. That was good. That was a good thing to do anyway. Error intro. And I think Ape has a similar video. If I go into incognito mode, I go to youtube.com. Error mitigation. There you go. So, so he's adding the noise. Mm. Mm. So those are the circuits to calibrate. Plot calibration. So mitigated counts, and he's doing basically the same. Okay, okay. So he's doing this is really what it's in the textbook. Textbook. Okay. Yeah. Okay. So this is basically that. That's good because I had that on my list anyway. Yeah, but of things that I wanted to do at some point. But it was cool. Pretty cool. Nevertheless, it doesn't seem to fix my problem. Yeah. See you next video.